Right. Hello, everybody. I'm Erica Bordy,
I'm Scott Mink.
I'm Kendall Asen.
and today we're going to be going over fluid dynamics of horizontal axis wind turbines. Okay, next. All right, so here to your right is an example of a horizontal axis wind turbine. A quick overview of how it works is it takes kinetic energy from the fluid to mechanical energy, as you can see with the spinning of the turbines. Then it produces it into electrical energy. Many things must be considered in a wind turbine, such as wind speed, blade design, and blade angle. Right?
Okay, so how horizontal axis wind turbines work. Horizontal axis wind turbines are usually composed of three blades attached to a central horizontal axle that drives a generator. To optimally capture wind power, turbines are equipped with a yaw system. This allows the turbine to turn into wind to capture the maximum amount of energy. Turbines might also be equipped with blade pitch controls, which alter its angle relative to the wind, known as angle of attack. This is changed depending on the current wind speeds. Okay, so the important equations. The power generated by a wind turbine is a function of air density, swept area, and wind speed. The most important variable of these is wind speed, as its value is cubed. There's a limit to power output known as the Betz limit, which is 0.5926 times the max power equation. However, this is only achievable with a theoretical wind turbine that has infinite blades, zero drag, and no hub. Okay. This is where design comes into play. Blade design, blade pitch, and swept area are all variables that are within our control as engineers. The optimal design for these depends on external variables such as atmospheric conditions and wind speed. These conditions can vary wildly from location to location and can even be affected by nearby wind farms. It is important to consider all of these things when planning wind farms. Okay.
All right. So the first peer-reviewed article we will be going over is the computational fluid dynamics performance analysis of horizontal axis wind turbines. The purpose of this study was to determine the max power generation through different design parameters such as the blade, wind speeds, blade angle, and other design considerations. Overall, the blade with a GE 1.5 XLE due to its common use in the wind turbine industry. An example of this turbine can be seen to your right. The author in this study used a simulation in SolidWorks of their design and compared theoretical calculations derived from fluid mechanics principles and theories to what they found. The authors found that both theoretical and simulations were both equivalent. Okay. So the major factor for maximum power generation, as showed by Scott earlier, is the velocity of air and position of the blade. Here are some examples of the blades they used in the study to your right. In this study, one of the parameters they varied is the blade's angle, otherwise known as the angle of attack. The authors varied this in order to determine the best lift and least drag. An example of this can be shown to your bottom right of your screen. Here it shows the lift force and the blade angle with reference to the wind. It also shows the wind's path along the surface of the blade. What the authors were able to find from this is when they started to increase the angle of the blade, it increased the lift force up until a certain point before it decreased. They also found effects from drag started to increase after the critical angle. The angle the authors found that produced the most lift and least drag for their wind turbine blade was 4 degrees. This was both shown in their SolidWorks simulation and fluid mechanics theories and calculations to hold true. Overall, this study showed that at a certain angle, the load is at a maximum, thus producing more power.
The second research paper we're going to look into is the development and validation of a CFD technique for aerodynamic analysis of horizontal axis wind turbines by a PhD student, Mr. Gomez Arati. The purpose of his study gives more accurate and better results for computational fluid dynamic methods, CFD, in order to bring better results for improved horizontal axis wind turbines. Their method for this study was the addition of wind tunnel computations as well as the blades and towers within their calculations. Results from the wind tunnel show that even though there was minimal influence on the power coefficient, the data led to the perpendicular sections of the tunnel be correctly modeled as well as the flow around the blade. Here in the image on the right, you can see the pressure on the walls at 6 different angles of the blade. Results from the blade and tower effects show that they achieved the flow details near the root of the blade and tower. They were able to determine the relationship between the tower and the wake effects of the blade, and they also received reduced values for the rotor thrust and torques. In the figure on the right, you can see the pressure outlines on the tower and the loss of torque through all different angles of the blade.
Okay, so wind turbines may have a large effect on our future. With rising energy demand and depletion of fossil fuels, energy from wind may be an important source. The energy that is made from wind is also a clean source and is relatively a cheaper alternative than other sources. However, there are some challenges to wind farms, such as location. Since wind farms take up a lot of space, they are mostly being used in rural areas with excess space and wind. Here are some examples to your right of wind farms, and as you can see, there needs to be a lot of space. The other issue is there is also not a lot of ways to transport the energy from these areas due to current transmission lines in the United States. However, with new advancements in technology every day, this source hopefully can be one that we can rely on for our future energy needs. Right? Thank you. And here is our works cited. Thank you all for listening to our presentation.